Welcome to this Nordic Tech webinar. Today we're going to talk about building ultra-tiny ML models for any wireless SoC with Neuton. We're going to do a deep dive into data collection using the lab.neuton.ai platform for automatically generating the tiniest of tiny ML models and a little bit about how to integrate these models into an NRF Connect SDK application. My name is Robin M. Saltness. I will be your host today. Together with me, I have Danil Zerebtsov from the Neuton R&D team that will walk you through the process of how to collect data and generating the Neuton models. After this presentation, we will have a live Q&A where you can ask questions. So the agenda for this webinar, quite quickly, it's a quick hardware overview and intro to the Neuton framework. Then we will do a demo of how you do gesture recognition using the Neuton framework, a model based on this framework. Then Danil will walk you through how to collect and prepare a dataset to build an accurate model and how to train and generate a Neuton model in the platform. And then we will touch quickly about embedding the model into the NRF Connect SDK application. So a few words about the Neuton framework. The Neuton framework is a unique framework for building ultra small ML models. The average model size for Neuton models is less than 5 kilobytes. And this opens up embedded ML and edge AI on devices that we thought previously were impossible. These models are up to 10 times smaller and more efficient than ML models that does the same task but based on other neural network frameworks. But they still retain the same accuracy. This is done via a fully automatic training process that grows a deep neural network until it reaches its maximum generalization ability and accuracy. This neuron by neuron approach ensures that only the necessary connections are made, which lowers inferencing times and removes the need for optimization, as well as allow the minimal size that allows it to run on anything as small as even a NRF 52805. For the demo today, we will be using the Thingy 53, which has the NRF 5340 SoC on it, completely overkill with all the flash and RAM that this SoC has. But it's very practical to run this demo on the Thingy 53 that has all the sensors built in. Today, we will use the accelerometer, and we will also benefit from the battery-operated platform itself. And with that, I will hand the word over to Danil for showing us the demo.
All right, so let me switch on the video so you guys can see what I'm doing here. Hi, everyone. It's a pleasure to meet you all. And before we dive into technical details of this webinar, we'd like to show you in action a machine learning model inside a Thingy 53 development board from Nordic and what it's capable of. So we've trained a model that consumes raw accelerometer and gyroscope data, 6 axes altogether. So we've collected this data previously and labeled it into 6 different hand gestures: swipe right, swipe left, double knock, double thumb tap, and then clockwise and counterclockwise rotation. And then we've configured these classes to control audio and video playback features on a computer, Windows or a Mac. So we've introduced business logic into the machine learning model outputs. So let's see how this works. I'm going to turn it on. And we can see here that it starts blinking. And let's see if it is connected. Okay, yeah, we can see that it is connected. And we're going to listen to some Mozart today. And let me switch over to this type of view so you guys can see everything in great detail. But before I do anything, I have to turn on the music. Okay, so it is playing in my earphones, but you can see the progress bar down here. You can see the seconds change. So let's go to the next track. Okay, sorry, I have to flip this over because this is how we used it to collect data. So, okay, next track. Okay, very good. Next track. Great. Now, let's go to the previous track. All right, very good. Now, let's see if it starts. Okay, it's playing right now. And double knock is going to pause it. As you can see, the seconds froze at 0.6. Let's do double knock again. And it's playing again. Now, double thumb tap is going to mute it. And once again, it has unmuted it. Now let's control the volume. So clockwise rotation makes it louder. Okay, now counterclockwise rotation brings it down. Okay, very good. Now let's pause it. And yeah, that's basically it. Let me switch it over. Switch it off. And here we go. Let's see if it disconnected. It has disconnected. Now it's a very simple concept, but a very powerful and compact model inside. And today we're going to tell you all about it. On this particular example, we have prepared all the necessary tools that will empower you to collect the data, to flush the firmware of this device, and then to test this on your own. And potentially you can use this example to pursue any other ideas that you guys might have. So today we're going to look at the practical example of how to embed the machine learning model into Nordic hardware. You're going to need four prerequisites. So the first one is the hardware. Here I've got one. Second is a development environment, and we've created a repository with all the necessary code to set it up. Then you need the access to the Neuton platform, which is luckily free, and I'm going to show you how it works and how you can create a machine learning model on your data without having to write any code or without, frankly speaking, without even knowing any data science. And the last is your time. Maybe in a few hours' time, if you have like an afternoon free, you can, using all this knowledge, build your own model and embed it into your hardware right away. Okay, so let's start with the development environment. So here we've created a repository for the project of remote control that you have just seen. And it includes all the necessary steps to set it up locally and to flush your hardware with the model from the Neuton platform. So you'll have all the links later, and here you can look at some description of the hardware and the software that is required, all the steps to configure this development environment locally, and also there are examples of how to run this model with the gestures that we have used to train it, because obviously you're going to have to repeat those gestures the same way we've been doing it when we were collecting data to make sure the model would recognize them. So here's how you should be holding the device because orientation matters. And here are the activities like swipe right, swipe left, different kinds of rotations, double knock, and double thumb tap. So it's very important to execute those actions the same way because otherwise the model will not recognize them. Now let's quickly see how to flush your device with this with all the necessary firmware so you could have the model embedded in Nordic TINI53. I'm going to switch over to VS Code where I have this repository open. And basically, it's very simple. So once you clone the repository, down here is a Neuton AI. In the source folder, there is a Neuton AI folder, and under the Neuton folder goes the model that you download from the platform. So here we have already included in this repository a compiled model that can recognize these 6 different gestures. And if you're going to be using this repository as an example to train your own model and embed them into your device, this is a good starting point because any model that you train on the platform just goes in here in the Neuton folder, and obviously you're going to have to do some amendments to the code so that it would contain the gestures that you have included in your own custom project. But to try out the model that we have pre-trained, you can basically clone it, have a piece of hardware, and get up and running in no time. Let me really show you how this works. So I've got a Nordic TINI53. It's connected by a USB cable, and here I've got a Seger, which is connected to another USB port. So it's working, and basically all you have to do is come in here, and obviously you're going to have NRF Connect plugin installed, and all of that is explained in the repository. And so all you have to do is build the project. I already did it before, but let's do it again. It's going to take just a few moments, and then you just flush it on your device and it's ready to go. Okay, almost done. Okay, now flush, and off it goes. After that, even if you had a device that you just acquired, which doesn't have any firmware, is going to be all set up to infer this model on device by connecting it to your computer via Bluetooth. And yeah, everything is finalized. Let me just turn it off. You have to reboot it every time after you flush it with new firmware. And yeah, now it's up and running. Let's see if I can connect it. I'm gonna go into the Bluetooth settings. I've got Neuton NRF remote control, connect. Okay, now it's got a green light. That means it's connected. And let's just open the music, play some song. So just give it a second for it to start playing. Okay, you can see the second counter in here. Again, it's playing in my earphones. But now if I do the... Okay, now you can see it's paused. I'm gonna hit it again. Now it's playing. So as you can see, everything works. So how would you go about collecting new data? And we encourage everybody to not only having all the knowledge that you will have received in this demo, in this webinar, not only just download the model and embed it directly into your device, which you can also do, but it would be much more interesting to try to collect some samples of your own data for these particular gestures, include that into the data set that we've already collected before, because we've used a few subjects to collect this data, and you would be the next subject, and then retrain it on the platform and see how that would perform. And obviously, if you include your data into the training data set, it should generalize on you much better. So let me explain to you how you can and how you should collect data for any use case, or this one in particular. So you can use the same repository, the same main C function, and here we've included one small comment. Basically, in here is the logic to flush the hardware with the model. But if you would need to collect more data, uncomment the line below and comment out the lines 133 to 151. This basically, let's just uncomment this and comment out these lines. So what it's going to do, it's not going to infer any model. It is going to just output the model predictions into the serial port. So you can see them in the terminal, or you could save them into a file. Let's connect the device once again. Okay, so here we go. I've connected it with USB Type-C, and then Sega goes in here. Now let's save this file with the changes, build the project once again. It's gonna take another few moments. And data collection is the single most important part of any machine learning project, because no matter what type of experience you have in data science or the machine learning algorithm that you are using, garbage in, garbage out. So if you don't have good examples, good training examples representing the activities or gestures that you are trying to distinguish with the model, it's not going to work. So you have to be extra careful, and I'm going to give you all the tips and tricks that are needed to collect the data in the most efficient way. So, okay, we've flushed this device with firmware that will just output the sensor data into the serial port. And let me disconnect the Sega here. And once again, I will reboot the device. So there is a button here. You can there is a toggle. You can turn it on and off. Okay, now it's running. To collect the data, we always recommend to use the cable because it's much more reliable. And let's have a look. So I'm just going to open my terminal and let's clear this. Also, in the repository, we've added just a few here in the README. We've added just a few commands for the command line interface, Mac OS CLI commands examples. So you have the device connected, right? So something is connected to your COM port. First, you need to find the name of the device connected to your COM port. So this is the command, lsl. Yeah. Okay, now it's giving us a name of the device which is connected to the COM port. So you copy the name of this device because for different ports is going to be a different name on different computers is going to be a different name. And the next command is output to serial port, and you have to use this actual USB device name in this command in two places, right here and right here. So I already got the correct device name in here. As you can see, it finishes with 2101. So when you click enter, you already have 6 axes of accelerometer and gyroscope in here. As you can see, once I start moving it, you can see the sensor data demonstrate the movement. So yeah, that's how you output the data into the serial port. But now you want to save it, and you want to do this for different gestures. So the way to do this is you run the same command and then T and just the name of the CSV file, gesture one session one CSV. This is how I'm going to call it. And before I start, there is an important thing to note here. So you would, first of all, how much data? For an experiment, uh, like in the demo that we have just shown, a few minutes of data for every gesture would be fine, would be enough. For like a proof of concept, where you would want this model to predict with decent quality on other subjects other than you who have been collecting data, you should try to add a few more subjects, other people, your friends and family, or somebody just to spend 10 minutes of their time to collect about 2 minutes per each gesture or activity. Also, you don't collect the data for all gestures and activities into a single file. Because you will then need to distinguish which part of your collected data belongs to which particular class, because then you were going to have to label the data with a certain class. As you can see in the terminal, you've got only axis XYZ for accelerometer and gyroscope. There is no label. So the label would be, just for you to remember, the name of the file. So gesture one, session one. And be ready to collect the data right after the data collection starts. Be ready to do the gesture. So I put my hand on the enter on the return key, and I start, and then I click the button and I start collecting data. So about 2 minutes or 1 minute would be enough. Let's say this time is over. So before I finish moving my hand, I will do Control C. That way, we make sure that you don't have in the beginning and at the end of your file with actual gestures some sensor data which doesn't correspond to the actual gesture. Like you don't start data collection, then start picking up your device because the data collection has started once you press the return key. So now I want to collect the second gesture. So I run the same command again, and I'm going to say this is going to be gesture 2. Okay. So I've got the device. I'm ready. And I'm collecting the second gesture. Let's say I'm collecting it for another 2 minutes, then Control C. And if it's a discrete gesture, like the one I was doing right now, it's better to have like a 1.5 second spacing between the gestures. I'll explain later why. It will all make sense. And then I have a third gesture, let's say it's gesture 3, and then I'm gonna do another swipe into a different direction. Okay, so I've collected the data. Now I have three files, three CSVs, which only contain the raw accelerometer and gyroscope data. What I want to do next, before I concatenate that into a single file, is to add a separate column, just a new column in every one of them, and give it a class name or class code, because it has to be an integer to be able to work on the platform. So the gesture one would be class 0 or target, whatever you want to call this column label. Gesture 2 would be class 1. Gesture 3 would be class 2. All the class naming has, or target naming has to start from 0 and consecutively up until the end of of the classes that you have. Another important thing to notice is that the model is going to always predict only what it was trained to predict. In this particular case, we have collected data for three classes, and it's going to predict the probabilities of those three classes all the time. But if your model is designed for production environment, and let's say it's a remote control for a smart ring or a smart watch, then you're not going to be, controlling your TV all the time. Most of the time, you are going to be sitting at the couch doing other things, and the model is still going to predict or output the probability of those three classes. And those are all going to be false detections. You don't want them to be, you don't want your TV start turning on or playing something when you are not watching it. So this means we need to teach the model what is the other state other than those gestures that you wanted to detect. We call this a random class or unknown class, negative class, doesn't matter. So you always have to collect a robust unknown class. So what I'd like to do for the start, because this usually is done in a multiple iterations, and I'll explain later why, but you just have your device in your hand, start data collection. Let's say we call it unknown or random session 1. And I will be doing the other things, typing on the computer, speaking on the phone, or just doing random gestures that are not a part of the classes that I want to collect. And how much data for the negative class? Obviously, in the most cases, in majority of time, you're not going to be trying to do the swipes and things like that. You're going to be doing other things. So it's normal to have 50% of your training data set or 40% consisting of this random class. I would start with 4 or 5 minutes, comparing to 2 minutes of the actual classes. And then you would expand it in further iterations. I'll explain how. So let's say we collected the random class. Let's stop. And another good thing to do is to also add an idle class, because technically it's also not the activity that you are trying to predict, but it's not really any motion, it's just laying there. So in order for the model to be able to distinguish the unknown and random, not to mix those things together, it's best to also add another separate idle class, because you might be just sitting idly with the slight movements of your hands, with your device in your hands, but it's not exactly, some kind of movement. It's an idle class. So the way to do this is, again, let's say idle. And first you have it sitting on the desk. Then you change the orientation of the device. You just flip it over and collect another maybe half a minute. You don't need much data for this class. Then try holding it in your hand in different positions, because there is a subtle movement comparing to laying on the desk. Okay, like this, and maybe like this, and then like this. And that's basically it. 3 minutes of this idle class is more than enough, because this one is easy to distinguish. So, and again, for the random class, you have to give it a label. Let's say the first three were 0, 1, 2. Then for the random class, it would be 4. Have a dictionary somewhere where you remember which class corresponds to which particular activity or random or idle. After all of that is done, then it's time to concatenate them just one by one without shuffling anything into a single CSV file. And let me show you what it looks like. So I've got here a data set prepared, and for this particular model with 6 classes. Let's just open it. And yeah, here it is. Accelerometer X, Y, and Z, gyroscope, and class. So all of these come from the file of the first gesture that I was collecting. Then goes the class. There are different classes in here. As you can see, they are in the class column, target column, whatever you want to call it. So the only requirement is for the CSV file to be in UTF-8 format and to have a header. So whatever you want to call your axes and your label column. That's all that is necessary to train the model on the Neuton platform. And let's close this. Actually, let's keep it open. We're going to need it just for a minute later down the road. Okay, so you've got the CSV file. It took you maybe half an hour to collect this data. And here's the platform. And this is the main workspace under My Solutions. And it's tile-based. So every card is a separate project, and it's here until you want to delete it. So you can always go back in there, look at the training results, download the model, and whatnot. So to create a new model, add new solution. So these are the 3 main tasks that we support. It's classification, be that binary or multi-class, like in our case. There is also regression when you predict a continuous variable like temperature, I don't know, pressure, things like that. And anomaly detection. So this one is an unsupervised machine learning algorithm where you don't provide any kind of label because you never know what the anomaly is going to be. So, and there is an explanation for all of them if you select it, but basically you need normal operational data, let's say of your piece of hardware. Let's say it emits some kind of vibration as it works. And if it breaks down, it would, start shaking, but you don't know how. So you just collect the data on the normal operation, train it on the model on the platform, and when in production, at inference, your device is going to start emitting different patterns, the model would flag it as an anomaly. So classification, let's give it a name, and click Next. Give it a second. Okay, so right away you can see the 3 main steps: upload the data set, configure the training, and download your model. It's very straightforward. You can just drag and drop your data set in here, select any of those you've uploaded for other models. They are also in here. Or if you don't have a data set, you just want to browse the platform. Here are some preloaded use cases. Everything is pre-configured in here. You cannot change any settings, but could give you a good idea of how the platform works. So we have a data set. You can just drop it right here. And as it is being uploaded, we're checking it for any problems it might have. For example, missing values are not acceptable. One thing I forgot to mention. And you can upload, it's always a single file. So all your data has to go into a single CSV. And you can upload either a CSV or an archive with one CSV inside, if it's a really big data set and you want to save time uploading. Okay. So the only thing that is required in the dataset tab is to select the target column. So here are your columns, and our target column is class. That's it. You can continue. But let me show you around a little more. So with a single data set that you have uploaded, we are going to split it into a training and validation portions into 80-20. We will train on 80, validate on 20, and use this data to understand and to show you the indication of the model quality. And if you have a separate holdout validation data set, you can use this toggle and you just drag and drop it the same way. Of course, the column names have to be the same and all, but that data will be used for validation. There is also an option to remove columns. Let's say you don't want gyroscope for this experiment, and you don't have to drop them from CSV files, just use these checkboxes here. The last one is session ID. So when you're going to be collecting a data for a robust model, it is going to have to include different subjects or different sessions. That means you are the same subject, but collecting data in different environmental conditions, like setting the device, holding the device in a different hand or something like that. So if that is the case, you have to have an additional attribute in your data set, or you should have, of course. You don't have to, but it would be much better if you indicate what is the session. And if it's different, if it's a different person, then it has to be a different session. Or if it's you, but collecting the data for the second time for this gesture, also has to be a different session. So if you have, say, 10 subjects that collected the data in one session, so your session ID would have 10 unique integers. And then you would indicate to the platform which one of those columns is a session ID, and the platform will use this data to split it into training and validation, putting different users in two subsets, making sure that it trains on one set of users and validates on unknown people. You might have a slightly lower uh, validation accuracy because you don't mix the subjects together in the training and validation data, but it's going to be a much more robust model because it will optimize itself as it validates on unknown users. So we don't have a session ID. Let's just click next. And we're done with the first tab. The next one is training pipeline. Okay, so two things to note here. So you can train the model on your pre-processed data set. So if you have some kind of very custom logic for data pre-processing and you know what you are doing, you don't want the model or the platform to interfere with that, you do not enable signal processing. You upload not raw data that we have collected, but already pre-processed data set where every row would constitute a training example. And you just train the optimized Neuton model and take advantage of the model size. But in our case, we're using raw signal data, so we need to enable data processing. And you can have a guided setup here with a small wizard, but let's use the manual setup. Now, the first and most important setting is the window size. And it's here in the windowing section. So what is the window size and why it matters? Let's go back to the data set. So by just using one sample, that's a point in time, you cannot know which gesture that might correspond. So you need to collect a buffer of sensor data where you are, doing a circle or like a checkbox or uh, any other gesture, and interpret that and give it an example to the model that this window of data of, for example, 1 second corresponds to class 0, and this other one corresponds to class 1. So the window size has to be the same for all the training examples that the platform is going to create. Basically, if you say, or if you define the window size to be 100, and I know that my sensor data collection was sampled at a frequency of 100 hertz, that means 100 records is 1 second. Then the platform will take the 100 records, create a training example, then another 100 records, and so forth. Now, another important thing to note here is a sliding shift. If you want the platform to augment more training samples from your data, then the platform has this setting here. And let's start setting this up now. By the way, there are two options: using the time interval, milliseconds and frequency, or the way I like to do it, number of rows. Simpler. I know the frequency, and I know the length in seconds or in milliseconds of approximately of the longest gesture. And I think that 1 second would be enough to distinguish any of the gestures that I was collecting. So I'm going to say the window size is going to be 100. And if I would want to create those training samples with an overlap, I would say a sliding shift would be 30. So it would, have an overlap of 70% between each of the new samples. But important thing to note here is that it's not always you can do a sliding shift for training, because those gestures that we have been just collecting, even though very similar, have one important distinction: a continuous movement. It doesn't matter where in the circle you start to collect the data for classification. It's going to close the circle anyway. So uh, this type of gesture, if all the data set was constituted of the type of data like this, let's say it's only two classes, clockwise rotation and counterclockwise rotation, then you can do the window creation with an overlap, no problem. But if you have a discrete movement like swipe right, which has a start and the end, that means that you would want to have in your training examples for this particular gesture the complete examples from start to finish. That means if you start doing the overlap in many samples, you are going to have parts of this gesture, and it's not going to be a valid training example. Another important thing to note is that after you have collected these discrete gestures, they're not going to be exactly 100 rows each, of course. So this requires a bit of pre-processing before you upload it to the platform. And we also do have a repository with code that does this pre-processing for you. It's a Python script that basically you tell it what is the window size, you upload your whole data, you use your whole data set with all the examples of all the gestures just before you upload it to the platform. And the only inputs in there are the window size, let's say 100, and you flag those classes which are discrete in nature. And it would iterate through the data for those classes and make sure that the actual motion that you're trying to classify goes exactly into the window in between, well, 0 and 100, so inside 1 second. So if it needs, it will do the padding for you. If it's too long, it will just cut it a little bit, but it will make sure that your actual signal is in the middle. And this way, after this data set is pre-processed, you upload it to the platform. And when you're going to say window of 100 and a sliding shift, of course, 100, because you cannot, do this with an overlap, it would, for those particular classes, have the exact examples of the gestures in the middle of 1 second window. Another thing is sliding shift for inference. So this doesn't impact training. Let's say you want the model to try to predict every 10 times per second to try to catch that window, and you just say this is going to be a sliding shift, and that's it for inference. And this is going to be a part of the archive. So the next one is feature extraction. So out of that window of 100 records for accelerometer, gyroscope, and all of these axes, which features are we going to extract to describe this signal? And by default, it's configured by on the platform as a perfect trade-off between accuracy and footprint. But you are more than welcome to try different things, or you can enable if you don't know any of this, you can enable all of them and then use feature selection, which will, before it trains the model, rank them by importance and not use those. It will just basically get rid of those that are irrelevant. There is also some heavyweight features here based on fast Fourier transform, and those are not, I cannot use them because my window size has to be the power of 2, so 128, for example. And then you can enable those if you wish, but they are usually used for vibrational data, maybe some sound data, things like that. You should not be really using them with activity or gesture recognition. So that's it for this part. And by the way, since everything is automated, you can try different combinations and then just retry them with other combinations to try to make a smaller model or a faster or a more accurate model. But the first thing we encourage you is to try just the default. Be more than enough. So in here, it is a multi-class classification since we have more than 2 classes. The input data is the platform understands the data on its own, but you still have control over this in case the platform made a mistake. So it's 16-bit integers. Evaluation metric, lots of metrics in here. Let's just stick with accuracy. Now, weights and coefficients, and all these 3 activation functions and output format. So if your device does not support floating point computations, then you should not be using this option in here. Or if you want the smallest possible model, use 8-bit quantization everywhere. So that would make the most optimal model. There are training stop options by number of hours, but it really takes much less. Maximum value of accuracy. Sometimes the model will continue training and uh, with very, very marginal increments to the accuracy, and you would rather have it stop and you can already start using it. So you can limit this by 0.99, for example. And maximum number of weights, any of those would stop the training. I'm just going to disable these. And the last one in here is the target hardware. So for the model packaging. So let's go with Cortex M33. That's it. You start training, and then everything happens on the back end without you. Well, basically, you just have to wait. And when this is done, and let's have a look at the pre-trained models. I've used that same exact data set just a while ago to be able to access the results tab. Okay, it's give it a second. So this one right here, I've trained it today. Let's go into the solution details. While this is launching, right now we can see data pre-processing. And this one has already been trained. And as you can see, it took 7 minutes. So it achieved a validation accuracy of 0.99. And here are the footprints, total footprint for RAM and flash. And they are not estimated. This is the compiled model footprint. Also broken down into the model in kilobytes, inference engine, which is the code to run the model, and signal pre-processing, which are those feature extraction functions that you have selected. And by the way, by looking at this, and 6.1 kilobytes is very small. You can run it on any hardware. But in case you want to make it even smaller or more optimal, you might want to go back and try to decrease this number, signal processing code, by just disabling some feature extraction options in your next run. And this would reduce this value here. Now, solution options. So these are all the checkpoints the model went through, and they're all these models are saved. And so this is not the best example of the idea that I'm trying to convey, but in some cases with complicating data, you might have a sharp increase in accuracy, and then very, very marginal improvements, but an increase of the footprint. And let's say by default, you're going to see the most accurate model, which is the largest one. But let's say you're happy with 98.5 accuracy, but the footprint is like more than half kilobyte less. You just click that, everything recalculates for you, and download the C library will download this exact model. And all of them are saved. You can then come back here and download any other model. Model quality is your target metric right here, and these are the other metrics. We calculate them anyway. This graph here also demonstrates this graphically. There is a feature importance matrix, and one way to use it is also to look at the bottom 10. And okay, here all the features are important. In some cases, you might have the bottom 10. Some of those features have zero importance. Again, you go back into you just launch a new experiment, disable that feature, and the model is going to be smaller, faster, less power, more power efficient. Another thing to assess the model accuracy is the confusion matrix, where you can see for each separate class what was the validation accuracy. You can see it's doing really good on all classes and falling a little short on class 5. And this brings me to my point that I touched a bit earlier. So how to improve on the model, because after you have trained the first model with your first set of data, usually that is not enough. So you download your C library, you embed it onto the hardware using the pattern that I've just demonstrated to you before with the GitHub repo and that environment, and then you start testing it. And you can see, for example, that, okay, so as you're holding, for example, the device like this, it false detects and it tells you that you are doing swipe right. It can happen, and it will happen in many cases. So you remember that as you're testing the model, and then you see that in this position, it false detects some other class. You remember that as well. And then you, again, collect more data for the random class by doing exactly what you were doing when it was false detecting, sitting like that, or whatever you were doing. because those new training examples are going to tell to the next model that this indeed is not swipe right, this is random, and this is also random. And you just add that at the bottom of your data set with the correct label as an unknown class or the random class, whatever you call it, and run another training iteration, test it again, make sure it doesn't false detects, and then maybe you catch another false pattern for false detection, and then you can shake it out this way by adding more random class data. Just make sure not to have 90% of your training data as random. I would say up to 50% is good enough. Start with a bit about 15%, 20 maybe percent, and then add more as you iterate. So here we have downloaded the model. Here it is. Let's have a look. As you can see, it has a Neuton directory, and it contains everything necessary to embed the model into your device using the example repository that we've provided. So here under the Neuton folder, you've got that exactly the same structure. So one more thing to note, in the artifacts directory, there is also inference runner folder where there are CLI tools for Linux, Mac, and Windows, which enable you to predict with the model on a CSV file on your computer. So it's a CLI command tool that you just feed the CSV file here in the README, everything is explained. And it would save the predictions for you and you can validate on your own. It also does validation on your holdout data set. So if you do not want to embed the model into your hardware to test it out, you can test it with this inference runner tool. Or the best option, really the most easiest one, is just to, if you are doing benchmarks with some kind of other platform or a product, and you want to run a benchmark in the same conditions using the same training and validation data sets, just upload the training and validation data sets on the platform, and you'll get that exact results you're looking for. So that's it. Thank you for your time, and we'd be happy to answer any questions you guys might have.
And questions we have indeed. Let's just start on the bottom.
Yeah.
Is the model created to download to the device? Does it use DSP if available?
So currently the platform is optimized for devices without DSP, but we are working on support for the devices with DSP functionality. So the current advantage of the Newton algorithm is that it doesn't even, as you have seen, the models are 4 kilobytes, 6 kilobytes in size. And to answer another question I see in the chat, so the inference time for this particular model is 1.4 milliseconds. It's very quick. It doesn't need acceleration, but it is going to indeed support DSP as well.
Then we have a question that I think I can answer, and this is, will this work on the NRF52DK or with a sensor or the Thingy52? And absolutely it will work. This sample, firmware sample, will not work out of the box because it's built for a Thingy53. So you would have to start with a sample that supports the Thingy52 or NR52DK and your chosen sensor, and then you download the C library and embed that into that application.
Hello, I'm sorry, something happened with my connection. Can you guys hear me?
Yes.
Okay, yes, I'm sorry. Did anybody answer the question, or shall I continue with the first one?
I answered this question.
Okay, all right, got it. So will it work on NRF52? It depends on the.
This I have answered.
Okay, cool. So let's go to the next one.
Did you have anything to add on the first one, or before you were?
Yeah, I'm just saying that we're working towards that, and currently the models are still. If you have seen the demo, 4 kilobytes, 6 kilobytes, and the inference time for that particular model is 1.4 milliseconds. It doesn't need acceleration, but of course we're working to support acceleration. So
then we have a question about I had an opportunity to attend a Neuton AI seminar in collaboration with STM. Does this mean that Neuton AI is now exclusive to Nordic and cannot be ported to other microcontrollers? And I want to add something there as well to start with. So the Neuton models as of today are downloaded as pure C libraries, and there's no plan on our roadmap to stop providing this as an option, which means we cannot not support other microcontrollers than Nordic ones. What we instead want to offer you is to simplify the integration into Nordic applications. So in the future, we will provide a solution that allows you to have a much higher ease of use if you choose to use Neuton models with Nordic hardware instead of other vendors.
There is nothing to add.
Then we can continue with let's see here. Are the features extracted by a separate model than the one constructed by Neuton AI's neuron by neuron algorithm?
So there are two steps into feature selection. The first one is a separate set of models before we start training the neural network, and it just excludes the most obvious features that would not make any sense to continue training with. And then there is a second step, which is done during training, regardless of the amount of features you selected. If the final neural network that you'll use in production does not find any value in some of them, it will automatically disable them, and your archive with the model will be also adjusted automatically, regardless of what has been selected during training. It will just not use those features and save your footprint, inference time, battery, and so forth.
Then there's another question about the different hardware. What would you have to change if you wanted to use the Thingy 91 or Thingy 91X instead of the Thingy 53? And here it's basically the same answer as with the Thingy 52 or the 52DK. The model that you use can be exactly the same because it's downloaded as a pure C library. But the firmware sample that we have been showing in this webinar, it's not built for the Thingy 91. So the easiest way to go is to find a sample for the Thingy 91 or Thingy 91X that you want to use and build the model into that by adding it to your source code and then calling the three functions that you need to initiate and run the inferencing on the Thingy 91X. Easiest is to start with a sample that already uses this sensor.
Technically, if you are sure that both devices have the same sensor orientation, and if you are using, you're holding it the same way, it might work. But again, you're going to have to adjust the code.
Of course, you have to collect the data for the sensor you're using and for the orientation of the sensor within the kit. Thank you. Let's see here. Without backpropagation or any other gradient-based update procedure, it seems that the only way to update the model is randomly and greedily connecting new nodes to the existing nodes. In what order are configurations attempted? In hundreds, thousands, etc.?
Well, if we were to follow this approach, then the model would be larger, not smaller. And as you have seen, the footprint, and hopefully if you guys try it out, you will see the difference. It is indeed much smaller. There is a much smaller number of nodes and connections between them. We have a separate slide, but I'll briefly explain this. And of course, it's a part of the secret source, which is patented, but it does not add more than necessary neurons. It adds them. It starts the training. There is no network architecture search. There is no number of predefined or architectures that we run through. We start with a single neuron. We connect it to inputs and train its weights. We have other interesting things like trainable parameters within activation functions, different parameters. Then, once having trained those weights, it would, if indeed the model doesn't overfit, it would add another neuron. It would connect it not necessarily to the previous one. It might connect the last added neuron to inputs. or to some neuron number 37, for example. So there is a different algorithm that defines the connectivity between the neurons. And having trained them one by one, it makes sure that every one of them provides input to the predicted accuracy. And also this ensures that there are no redundant nodes in your predefined architecture, which could be any value and it would not impact the outcome. So I wish I could tell you more, but these are the main highlights.
Then there's a question about do we plan to extend the pipeline to support vision data in the near future, and what is the biggest challenge to doing so?
So we are planning to extend into the vision, but the first one is going to be audio data, which is in the roadmap. No challenge really, only the development time. We having identified the the best thing about our algorithm being the smallest possible footprint, we decided as a business decision to target the most constrained devices and bring value for them. And of course, we are extending into more different modalities. Currently working on audio, and then video will come later.
Then there's a question from the chat. Is the Neuton AI platform more suited to certain types of data?
Mm-hmm. So it is any type of time series sensor-based data is applicable. So in our example, accelerometer and gyroscope, you can have radar data, electrical cardiogram data, PPG, light signal, capacitive touch sensor, resistive sensor. All of those we had experience with. As long as it is time series sensor-based data, whatever it is, temperature, it is applicable.
There's another one from the chat. Does Neuton include data pre-processing, and is it supervised or automated?
So as you have seen in the demo, of course, it does do data pre-processing. That is what we configure on the training tab. What is going to be the window size of the data to extract the features? Which features to extract? Is it going to be on overlap or not? And it's a major part of the solutions, how we call them, not just the model, because the model trains on the data that makes sense, that provides insights in between the data that you supply for a certain class and the actual class. And there are two things to keep in mind here. First, it has to extract features that provide value for the model to learn from. And second, you have to extract them in the most optimal way possible. Both of those things are the major guidelines in our development process. And whatever features that you select on the platform, all of them are highly optimized without any third-party libraries. Everything is written from scratch in-house using only our code and doesn't have any overhead. For example, like some math library, which might have so many other things that you are not going to need at inference. So none of that is included into the code, and which makes it really optimized.
So here's a very hands-on question. I want to train a classification model, but the classification are strongly skewed towards the first classification. This is reflected in both the data I recorded and the actual data it will be measuring. Should I keep the training data skewed, or should I make the training data more balanced?
So this is indeed a million-dollar question. We have tried all the different undersampling, oversampling techniques, and there's like 80 different SMOTE and SMOTE and other methods, of course. And in short, none of them work as intended or as expected. So the model outputs the probabilities, the predicted probabilities of a certain class. And this type of problem, unbalanced target classes, is handled at a post-processing step. In your C code, you would then treat certain probabilities as certain classes. For example, you will raise the threshold for predicting the minority class. And also, in addition to that, you would introduce a step to maybe have two consecutive predictions of this class because your window moves at a very small step, for example, like 10 times per second. And then you would need the model based on your experiments to predict with this threshold, this class twice. And that would increase the confidence in predicting that class. There are lots of ways you can work with post-processing, and we generally recommend users to work with the threshold. Because in real life, if this, one other thing to note, this is also very important. So if this is just the characteristic of you collecting the data this way, try to think about real world applications, how skewed the data is going to be there. If statistically this second class, it indeed is going to be a minority class, then it's great, work with thresholds. If it's the opposite, then you should rebalance your data.
Then there's a question I want to try. I'm trying to train a model to classify the multiple trends in pressure versus compliance data. However, both the pressure and compliance data varies with each run. Is it possible to train a model on this data, or will I need to extract features?
So the platform will extract the features for you. If I got the question right, for certain, let's say you have certain conditions you are trying to classify, I don't know, operational modes 1, 2, and 3, and the distributions and different patterns in your features in your raw data have a high degree of variability, but they are not random, I presume. They correspond to a certain class, and there are certain patterns there which you can, well, have the model pick up. So the best way to do is to try to collect as much data as possible, preferably from multiple devices, because they might have different patterns, but then use the platform with a certain window and try different features. For example, you can try some heavyweight features based on fast Fourier transform and spectrogram. If it's like high frequency data, something like a vibration analysis, but you said pressure and compliance data. I'll go with traditional statistical features for the start and see how it performs. But the main takeaway here, the more examples of certain conditions you provide, the better the model will find those patterns.
Then there's a question if other inputs can be used for the algorithm, for example, quaternions or the magnetometer to be used in conjunction with the accelerometer and gyroscope.
Sure, of course. As long as the data sampling frequency, if it comes from the same sensor, for example, accelerometer, gyroscope, and magnetometer, and it's synchronized as according to the timestamp, then yeah, sure. If it comes from different sensors and it has a slight deviation in timestamps, then you could do some pre-processing to interpolate the blank spots in between them and just have them represent the same window. But yeah, sure, any data is applicable.
Then we have a lot more questions, but I'm going to do a selection for the last few ones, so we get through the entire webinar. First, I want to do is when should the model use 8-bit quantization, 16-bit, or 32-bit float? What is preferable for the NRF52840? And the NRF52840, just by the way, has floating point unit.
Okay, so this really depends what you're going for. So like a rule of thumb is to use the same type of quantization as your input data. For example, if you have 16-bit integers, then the best performing model should be 16-bit quantization. But of course, if you want to reduce the model size, 8-bit quantization can work too. And again, depending on the use case you're solving and the types of patterns in the data, either one of them could provide maybe a marginally better or worse result. But generally speaking, all of them will have comparable accuracy. So just select based on your experiments and the footprint that is required. If you have a very powerful hardware, then I mean either one of them would work.
Yeah, then we're also going to answer Would you consider the framework from input data to final model a form of model distillation?
Well, very generally speaking, a model is like a form of data distillation. You just capture the most important things and reflect them in weights. But technically, there is no model distillation. We don't train a large neural network and then compress it. None of that happens. It trains, as I mentioned, one neuron by neuron, and it is always going to be a unique structure. Even if you use exactly the same data set and just delete there a few samples, it will train a completely different architecture. It's not even under our control as engineers. When we're working on some custom projects, like a really hard stuff, the most effort goes into the data pre-processing. If there are some features that are really custom specific to this type of data, but never do we go as engineers into the algorithm and try to tune anything in there. All of that happens automatically.
Then there's a question, can you load and simultaneously process multiple models on the same host corresponding with different sensors?
If you mean at inference, well, if your hardware supports, I don't know, multi-threading, multi-processing, then of course, yeah, these models are very small. You can, if you have the real estate, you can, for example, we've had a use case with two sequential models, one running after another. It was a case of arrhythmia diagnosis, and we were working with electrical cardiogram data. And the first model, it was a binary classifier that would say, is there a probability of the subject having arrhythmia or not? And if yes, if the first model says 1, then the second model kicks in and then takes that particular input of data and then uses a second model to classify the kind of arrhythmia. There were 5 kinds of arrhythmia in that use case, easily.
Then there's a question, can you load a model to the device over the air, or does it have to be built into the device firmware at compile time?
Well, if you, basically we provide you with an artifact. And as an example, in this webinar, we provided you with a development environment. If you have some kind of your own CI/CD process, you're free to just use that model in your repository and have your pipeline, updated over the air.
Then there was one question here. I wasn't planning to talk about this, but since it came in, I can answer a little bit here. What are the most advantages of Neuton compared to Edge Impulse? So Edge Impulse has been a Nordic partner for a long time, and it still has a place in the Nordic ecosystem. But I've actually prepared a slide in case this question came up. And here we have it. So Edge Impulse is using a completely different framework. They are using open frameworks like TensorFlow and Keras, whereas Neuton uses their own proprietary algorithm to grow this deep neural networks automatically. So Edge Impulse requires you to have a little bit more know-how into how you select the parameters to make a successful network, whereas Neuton handles this automatically for you. So this makes the Edge Impulse framework have a different organization to their models, which also require you to optimize them after they've been built to be efficient. This makes them suited for hardware acceleration, whereas with the Neuton models, they are optimized by default because them builds these models to be only as efficient as the minimum amount of neurons will make them, which makes them smaller, makes them execute faster, and most importantly, where we have only suggested Edge Impulse models for the NRF5340, the NRF52840, and our higher end SoCs in each series. the Neuton models can run on any SoC down to the NRF52805, even NRF51 series processors. So these are the main difference between Neuton and Edge Impulse as I see it. But Edge Impulse still has a place in the Nordic ecosystem, and we will continue supporting Edge Impulse, and we hope Edge Impulse will continue supporting us as well. And with that, I think we will have to call it for tonight. We are 10 minutes over time. Thank you all for watching. It has been a pleasure to have you here. If you want to watch more webinars, or if you want to see this as a recording and access the slides and access the links to the repository to download the sample code shown, you can go to webinars.nordicsemi.com. I recommend the Cephy webinar that is next week. See you soon, and have a good day, evening, or night.
Thanks, everyone.
Then we will do a Q&A, and there is a few questions in the questions box. Let's see here. How is Neuton's licensing policy?
Yeah, so the access to the platform is free for all the developers. You guys can come in, register, you just sign up, you get access, and basically start training your models. There is no production licensing. You basically can use this platform to train a model and use it at your discretion as an experiment or as a production model.
Then there's a question about what is the main difference between Edge Impulse and Neuton?
Yeah, so we get
gesture recognition and sound identification and predictive maintenance is also possible with Edge Impulse. Is Neuton just smaller in memory, or is there anything else I need to know?
Okay, so let's go one by one. So how does it compare to Edge Impulse? We get this question quite a lot, and frankly speaking, we've been running tests with all the competing platforms, and there's more than Edge Impulse out there. So for years, we've been running those tests, and those are all beautiful platforms, very mature products. But there are a few differences. So the first most important difference is the footprint and inference time. Since all the other platforms and frameworks basically use the well-known algorithms like a TensorFlow model or a PyTorch model, they all have their own sort of limitations of how small they could be, because they have been around for quite some time, and all the compression techniques are well known. They can just compress up to that particular limit. We are not using neither of well-known or open source frameworks. Under the hood of Neuton is a proprietary neural network algorithm. For example, if you guys are into machine learning, we don't have back propagation of an error. There is no stochastic gradient descent. And there is no deep learning framework in the world other than Neuton that doesn't use those technologies. And given the fact that we have developed this framework completely in-house, we've with the sole purpose of running on embedded devices, we made it possible to have a resulting model at least 10 times smaller than any of those frameworks. And you can basically, you're free to use this very dataset or any other dataset that you can find online to try to train the same model on either of those platforms and on Neuton, and just compare the footprint on your own. We have a very extensive study with hundreds of benchmarks where in none of the cases, neither of the competing frameworks have achieved the smaller model. Even by a factor of 5 at least, there is a difference. So in terms of other questions, you said
there is a question. There's a question here about what is the architecture of the gesture model that you showed? What's the number of layers and the data types?
Yeah, that's a great question. And I think I have a slide here. Just a second. So there is Let me just look it up. Before I open it, that's the main difference. So our framework is patented. We have 2 patents because it does not have any layers. There is no basically. Oh, okay, I found the slide. Let's look at this slide for a second. So I'm going to share the screen. Okay, hopefully you guys can see it. This is what we use for our presentations. So this is a traditional fully connected perceptron, or any other network for that matter, of the well-known architectures. So the beautiful algorithms for many things, very powerful in large language models, image classification, things like that. But when it comes to embedding into edge devices, they have a few limitations. The main one is the architecture concept. Even before you start training the model, you don't know how well this is going to do. You will define number of layers, number of nodes in the layer, and you know the footprint before you start training the model. You know how many connections, how many nodes there are. Okay, you can just subtract some percentage for the dropout later, but you already know the size of the model. Okay, let's say you've done a few iterations with different architectures and you've trained the model that satisfies your accuracy criteria. And then you go ahead and start compressing it, pruning, quantization, compression, convert it in TensorFlow Lite Micro, and start using this. But and it performs well, but you never know how many nodes in this neural network are redundant. We have seen in our studies examples of 50% of nodes being redundant. That means these neurons could be missing, and this would not impact the accuracy. But you cannot get rid of them because it's a fixed neural network architecture. They introduce weights, biases, they impact the footprint and inference time, and you're basically stuck with them. So the way Neuton trains, there is no architecture. Nobody defines it. There is no neural network architecture search. It starts, these are your inputs, these are your 6 axes. It starts with a single neuron. It gets connected to the inputs. It trains the weights of this neuron without, as I mentioned, without backpropagation, without stochastic gradient descent. We have our own optimization function, which we have developed. It's a global optimization algorithm, and it has been patented. So after this, the weights of this neuron have been trained, the framework automatically decides, okay, there is more room to train. It doesn't overfit yet. It adds a new neuron. It makes arbitrary connections between other neurons if necessary. It has its own built-in algorithm for network connectivity. It may even connect the last neuron, like in this case, to the inputs, to certain inputs, to certain other neurons. So it adds neurons one by one by freezing the previous layers and only training, or not layers, the weights, and then only training the weights of the current neuron it is working on. This way, making sure that every single neuron or the node of the network that it adds brings the value for the output. And when it starts to overfit, it automatically stops adding neurons and stops training. And this ensures that there is no redundant nodes, and out of the box, without pruning, compression, or quantization, this is going to be at least 10 times smaller than this. There are many other things, like, for example, there are additional trainable parameters within activation functions, algorithm built in, and all of that happens automatically. Even our engineers working on custom, very complex projects, we don't go inside the algorithm and configure it. It does everything on its own. Okay, so I hope I answered that question. I'm sorry for taking too much time. All right. Other published performance comparisons results with other frameworks. There are a few on the website. There's no white papers for that matter, but if any of you guys are interested, we can set up a separate meeting and show you all the benchmarks that we have. By the way, we've made those benchmarks transparent. It's not just a slide we're going to show you. We will give you a repository with all the data, with all the settings for all the platforms, with all the models we've downloaded there. And you are free to go and, test it and make sure that the benchmarks that we're showing to you are accurate. Okay, I'm just Rob. I'm going one by one. I'm looking at the questions. So how? And by the way, are we over the time? Do we have any more time?
We can continue.
All right, cool. So how modular is the Neuton pipeline? Can parts of it, feature extraction, model compression, be decoupled and used independently? Well, during the demo, I've showed you how you can disable feature extraction option and just use your preprocessed data set to train the Neuton model. So that's one option. But and there is also, by the way, on the platform, let me show this to you. So yeah, I could say that you can decouple this. There is no like specific action buttons on the platform, but you can, for example, let me share the screen. Okay, so after you train the model, it's gonna give you the process data set, the training part and the validation part. You can look it up like this. So all the features that you have selected had been extracted, and here they are. And this is what the model was trained on. And you can just download it and run your own experiments. Okay, and just to remind you that the data set was just 6 axes of raw data, but the pre-processed data set includes it all. The secret, and we're free to distribute this to everybody. The secret sauces and how those features are created in the most optimal fashion. So you are free to download any of these data sets and try the model on your own. Or you can go and upload your pre-processed data set in here and then disable the signal processing pipeline and just train the Neuton model. Okay, I hope that answers the question. So is the platform service free to use? Yes, it's free to use. There is no costs. So how is the model transferred into hardware, for example, Thingy 53? Well, I think we covered that in the first part of the demo. So we will distribute the links to the repository. You guys are free to come check it out. And there is an example of how to flash the firmware of the device with this particular model. And you can modify that after having trained your own model on the platform and just use that same repo to flash the hardware. So on the target, what was the average RAM consumption you have observed in percent when you apply such algo? I'm not sure I quite get the question, but well, for this particular model, if we're speaking about this one, let me pull it up. I think I have it somewhere here. The RAM consumption here is 1.4 kilobytes. And the RAM typically is going to be the size of the, of the signal processing code and the buffer of the window that you're going to use. If you have a very wide data set with like 100 sensor features and
Okay, it looks like we lost connection with Danil.
the price, there is no price, so it's free for everybody. How does the platform compare to HMBOS? Okay, we've discussed that. Can you teach the model offline, or it works only through the website? Unfortunately, you cannot teach the model offline because you need well, the environment necessary to run this model. Of course, you need the algorithm, which is our secret sauce, and you need compute, and all of that is provided to you guys for free. You just all you have to do is bring your data to the platform. Okay, so if you have multiple repeated gestures in one file, how you mark where each gesture starts? Do you need to mark data between gestures as idle state? So you don't. Okay, so if all your gestures are continuous, you don't have to worry about anything. Just collect the data. Let's say gesture 1, gesture 2, whatever else, gesture 3, concat them together, and random gesture also goes at the bottom. Idle gesture also goes as a separate class, and you just feed it to the platform. When you have discrete movements, and let's say you have 5 different movements in there, the biggest one of them is roughly 1 second, there is some pre-processing involved, because when you collect the data, it's not going to be exactly 1 second every time. and some of them are going to be bigger, some of them shorter. So we also have another repository with Python code that more or less automates for you the process of pre-processing your raw collected data. The only input is that from your head is that, okay, so 1 second or 1.5 seconds is the biggest gesture. So that's the only configuration parameter. And also you defined which classes in your data set are discrete. Let's say you have this class, which is not discrete, and this class. This is class number 2. So in this code, you define the number of the length of the window and the classes that are discrete, and it would automatically find those training examples with the discrete classes and either pad or subtract the sensor data to make sure the actual signal is in the middle of the window of, let's say, 100 records, like in our example. And then you go onto the platform and use that same window so that when the platform cuts the data into segments, when it reaches that particular class, it would have exactly centered examples in each one of the training samples. Okay, I think we've got them all. What do you say, Robin?
Yeah, I can. Let me see here. I need to change my. Yeah, I think I can touch a little bit on the how do you transfer the model to the hardware of the Thingy 53 processor. So you download the model as a normal C library, which you have to put it into a custom Thingy 53 firmware. There's only 3 function calls that you need to do, but you have to also remember to include the library in your code.